This presentation is for non-line-of-sight surface reconstruction using the directional light cone transform. By Sean Young, David Lindell, Bernd Girod, David Taubman, and Gordon Wetzstein. Non-line-of-sight imaging, or imaging around the corner, is an emerging technology, with potential applications for self-driving cars, remote sensing, and medical imaging to name just a few. This challenging problem can be solved using time-of-flight imaging systems, with highly sensitive photodetectors and ultra-fast pulse lasers. The sensor measures the time it takes for a laser pulse to propagate to a wall, around the corner to the hidden object, and back. Reflected photons from each object are captured by the sensor over time. And by scanning multiple locations on the wall, the hidden object can be recovered. Recent non-line-of-sight surface reconstruction methods have shown promising results. However, they still have a number of drawbacks. These include sensitivity to algorithm initialization or capture noise, and high computational complexity. Moreover, they can fail to reconstruct the scene altogether if the scene geometry is complex. We propose the directional light cone transform for reconstructing non-line-of-sight surfaces. Our approach jointly recovers hidden scene albedo and their surface normals, based on which 3D surfaces can be reconstructed. Our method is orders of magnitude faster than similarly based surface reconstruction methods, and robust to background noise that is present in practical capture environments. Let us first review the confocal volumetric albedo model, proposed by O'Toole et al., which reconstructs the hidden scene as a volume of albedo. Here, a location, x', y' on the wall, at time t, captures albedo ρ from all scene locations x, y, z, which take the pulsed laser half d seconds to reach from x', y'. In matrix notation, this simply becomes tau equals k ρ. Although this is a linear model, computing the hidden scene albedo ρ from tau, by directly inverting the system, is challenging due to the size and the unstructuredness of the system matrix K. The idea behind the light cone transform is to warp the measurements tau, and the hidden scene albedo ρ. This expresses the forward model as a convolution, allowing us to recover the hidden scene albedo from the measurements using deconvolution. Unfortunately, the volumetric albedo model is agnostic to the surface normals of the hidden scene, and does not facilitate recovery thereof, which we require for surface reconstruction. In this work, we propose the directional albedo model, which can be inverted efficiently to recover the required surface normals. We introduce surface normals into our model using Lambert's cosine terms. Now, the same location x', y' on the wall, at time t, captures albedo-scaled normal vectors projected onto the light path, from scene locations which are half t light seconds away. We refer to these albedo-scaled normal vectors as directional albedo. In matrix notation, we now have tau equals ks, upsilon. This is again a linear model due to the linearity of the projector S, and the sensing matrix K. However, recovering the directional albedo upsilon from the measurements is still difficult, due to the size and the unstructuredness of the sensing matrix K. The idea behind the directional light cone transform is to warp the measurements tau, and the unknown directional albedo upsilon. This allows us to express the forward model as a sum of three convolutions. Notice that since we have only one equation for every three variables, standard deconvolution cannot be used to recover the directional albedo from the measurements. Nevertheless, we can pose the recovery of directional albedos as a regularized least squares problem. The optimality conditions of this problem give us a 3x3 block system of equations, where each block is either a filter or a signal. Therefore, we can solve this system of equations using block Cholesky decomposition, performing the associated forward and backward substitutions by filtering the intermediate signals in the Fourier domain. Having recovered the directional albedo, we reconstruct the hidden scene surface by fitting a manifold onto the recovered normals. Here, we show the surface fitted on the simulated Serapis and Bunny scenes. Here, we now show the surfaces fitted on the captured S and U, and discus thrower scenes. Quantitative and qualitative comparisons with other methods are available in the paper. We believe the directional light cone transform is a big step for non-line-of-sight imaging, providing a practical way to estimate the hidden scene surface normals needed for surface reconstruction.